Today we venture into chapter 4, logarithmic functions. These can be a little weird. I'm going to try and put them in context, and so hopefully that will help. If you recall, at the end of 3.1, I gave you this equation and said, well, we don't have a way to solve that yet, but we'll get there in chapter 4, basically. So logarithmic functions are what allow us to solve for the x that's in an expression like this. So the x is in the exponent, and there hasn't been a way so far to find it, like actually isolate it. Logarithms are going to allow us to get that x out of the exponent and actually solve for its value. So anytime that you see an x in the exponent, use logarithms to get it down. Basically what a logarithm is doing is it's undoing the exponential operation. So an exponential takes it to the power x, and the logarithm is taking it out of the power x and pulling it down. So they're paired to each other in terms of the growth factor of the exponential. So both of them have that same a value in order to undo each other, because basically the logarithm will undo the exponential and the exponential will undo the logarithm. What we call that is they invert each other. So for an example, if you had 2 is equal to 10 to the x, you would want to use a log base 10 in order to undo the 10 to the x that we have here. Now, if on both sides of this equation, so if I take a log base 10 of 2 and a log base 10 of 10 to the x, then the log base 10, which I've underlined here in red, and the 10 to the x, the log base 10 and the 10 to the go away, and all I get back is my exponent that's circled here, the x. I just get x back. They literally cancel each other. I think what makes logarithms weird the first time around is that this is a function that is entirely defined by its relationship with exponentials. And so it's weird because you have words instead of just letters. And it's a little weird because you just learned exponentials, and really this logarithm is just going to get rid of the exponential term and make it linear again. So because they arise so much in nature, we have to talk about them, and we have to find a way to actually solve for that x value that's in the exponent. And logarithms are the thing that allow us to do that, so that's why we use them. Now, I can generalize this. I gave you a specific example with numbers to any exponential where y is equal to some a to the x. If we use the logarithm with base a, we can undo that a to the x to get back our x value each time. The logarithm that you as students are most likely to run into and in your fields is probably log base 10. It is the most widely used in chemistry and in biology. So it's become so common that it's written without the base. You just write it as log. So if you ever see log, you just assume that it's log base 10. The one that's on your calculator, that's log, that's log base 10, because it is that common. It's built into your calculator, which allows you to then just evaluate some values. So let's see, what is log base 10 of 0.1? For example, if you substitute that into your calculator, you should get a -1 out. Why do you get -1? Well, 0.1 is 10 to the -1 because it's 1/10. And so, since that's 10 to the -1, the log base 10 of 10 to the -1, the 10s go away and the log goes away, and you're left just with your exponent, that -1. Okay? So what about log base 10 of 100? If you substitute that in, you should get, in that case, a 2, because 10 squared is 100. Okay? Now, not all of you are going to have a more general logarithm, which is log base A or log base B, I think is what your calculator calls it. So you have to consider, we're just going to talk about some simple cases of other logarithms, just to give you an idea of how these are working. So, and by simple, I just mean smaller a values, things that you could easily check. So if I took log base 2 of 8, We've done a lot of 2 to the this and that. So 2 to the what gets you 8 is really the question that you're asking when you take log base 2 of 8. What power of 2 corresponds to this value? And in that particular case, if you plugged 2 to the 3 into your calculator, or 2 cubed, you are going to get 8. And so the value that you should get out for log base 2 of 8 is then 3. Okay? I hope this is making some sense. Log base 3 of 1/9, what about that? So 3 to what power gets us 1/9 is really what we're asking. Now, if you think about that, 1/9 is 1 over 3 squared. So since that's in the denominator, that's the same as 3 to the -2. So you should get a -2 out. Okay, and then I wrote it all here too. 3 to the -2 is 1 over 3 squared, and that gets you that 1/9. That is consistent with our input. Okay, last little one here. Now, what if I have log base 4 of 2? So now I'm saying 4 to what power gets me a 2? Well, 2 is the square root of 4, so, and if we recall that our exponents that are fractions correspond to roots, then the square root of 4 is the same as 4 to the 1/2. And so in this case, you should get a 1/2 out, or a 0.5, depending on the output of your calculator. It's probably 0.5. And then as I showed you here, 4 to the 1/2 is the same as the square root of 4, which gets us our 2. Hopefully, these are getting a little bit more comfortable with more examples. Now, properties of logarithms. So because of this relationship with the exponentials, there are specific things that we can define about all logarithms, regardless of base. And the first one of which, that you may have noticed when we had our exponentials, when does your exponential give you a 1? So log base a of 1 is equal to what? So a to some power always gets us 1. And what power do we raise a to that always gets us 1? If you recall from when we did exponentials, if I have a 0 for my x value, a to the 0 always gets me 1 for any value of a in the defined a range that we've had, which has been greater than 0. So don't worry about any of the other cases, but as long as a is greater than 0, that's going to be the case. Now, log base a of a, what about that one? So in that case, a to the what equals a? This one is a little bit more straightforward because you have an a and you have an a here, and the power, when there's no power listed, is a power of 1. So a to the question mark equal to a just means that the power in this case is going to be 1. So if you plug in the same number into the logarithm as its base, it's always going to give you a 1. And then the next one here is log base a of a to the x. Okay, so in this case, I'm asking the question, a to the what, where a is the base of the logarithm, is equal to a to the x. Okay, well, they both have base a, so their exponents must be the same, which means that the question mark in this case must be x. So a to the, because a to the x has to equal a to the x, it's not going to equal a to the q unless q is equal to x. So it allows us to effectively pull that exponent out, right? This is what I was talking about with the numbers. Similarly, because these invert each other, because the logarithm undoes the exponential also undoes the logarithm. So if I take a to a logarithm power with a base of a, so a to the log base a of x, I'm just going to get back my x value again, because the exponential and the logarithm cancel each other, and I'm left with x. So these things are very big. They're going to allow you to simplify and solve complex equations that involve exponentials and logarithms, ultimately. So getting comfortable with these things, there's a reason that I'm giving you as many, multiple examples of what I'm talking about and how it breaks it down, because I know that this is a topic that people struggle with. And you have to just remember that the log base a, log base a, is a function, just like f of x was. It is a function, that it just has a specific base. So you can't do anything with them independently. They have to act on something in order to apply them. I think for visual context, it's good to take a look at these graphs. So let's take a look at the graph of y equals log base 10 of x. Graph it on your calculator. You have log built into your calculator. Just plug it in and compare with what I've sketched here. You can also compare it with 10 to the x. Now, what I've drawn here, you can kind of see that there's some symmetry here, right? 10 to the x looks a lot like log base 10 of x, just flipped over this dotted, well, dashed orange line at y equals x. These graphs are very, very related to each other. In fact, the inputs of log base 10x are the outputs of 10 to the x, because that's how logarithms are defined. So in this particular case, you can see that there are no negative x values that work for your logarithm. You can't plug them in. And the reason for that is because 10 to the x is always greater than 0. Look at the output of 10 to the x. It's always greater than 0. So you can't have a negative input into your logarithm function because it wouldn't be consistent with how they're defined. Now, and then I wrote here about that flipped across the orange dotted line at y equals x. This is a characteristic of all inverse functions. Anytime that one function undoes another function, they're going to have this kind of symmetry in their graphs, which is really nice to visualize and just kind of get a peek. We'll talk more about it for more general functions in the future, but I feel like while we're defining the logarithms in terms of these exponentials, it's really important for you to see how these two things are related to each other. So that's why I drew it. Now, as you probably saw with the log base 10, if a is greater than 1, this graph resembles the same form that I just drew. They're both increasing functions, and they look kind of like your default exponential. Now, if your a value is less than 1, still greater than 0, because that's how we define our exponential bases also, the graph gets a little flipped, right? I sketched in here 1 over 10 to the x in the purple. And as you can see, right, that flipped the whole graph over the y-axis, if you recall from chapter 3. And then we still flip over the y equals x dashed line here, right, in order to get the green graph, which is the log base 1/10 of x. Luckily, you don't deal with these too frequently, but it's important for you to get a visualization of what that means, why it's different. Notice that both of these functions are decreasing. So if your a value is less than 1, with an exponential, you remember, you're multiplying by a fraction. You're getting a fraction of the population that you previously had every time. Whereas with the logarithm, it's going to correspond similarly. It's also a decreasing function on the interval. Okay? And the last thing to talk about is just reminding you that when you're plotting graphs, so if you have to sketch something, build a table. You can still build a table with these guys. So if I were trying to graph f of x equals log base 2 of x, I would frankly take a look at my exponentials and then use those exponential values to build a table for my logarithms. Because the exponentials are more graspable. They're easier, they're more tangible for you to work with. So I put a reference column over here just on the side as I'm doing base 2, so x is 2 to some power in each of these cases for me to graph it. So I did my -2, -1, 0, 1, and 2 in order to build the graph, but I did it with the exponentials to construct the x values that I would then substitute into log base 2 of x. So 2 to the -2 gets me 1/4. I'm going to change highlighter colors because I want to make sure these things are distinct. So 2 to the -2, right, gets me 1/4. And then I take that 1/4 and I would substitute it into my log base 2 of x. But when I substitute 1/4 into log base 2 of x, what I end up with coming out is that -2 that I plugged in to the exponential, because the logarithm undoes the exponential, and so 1/4 is 2 to the -2, log base 2 of 2 to the -2 gets me back that -2, okay? I'll explain the next one and then wrap this up, but so then I was like, okay, so that's my -2, my -1, 2 to the -1 gets me 1/2. If I then take that 1/2 and I substitute it into the equation, changing colors a little bit again, then that 1/2 is 2 to the -1. Log base 2 of 2 to the -1. The 2 to the and the log base 2 cancel each other, leaving me with the -1. Does that make some sense? I hope. It is, for me, I feel like this helps you use the context of what you do know to construct data that you can then build the graph from. Now, if you have log base b in your calculator, you don't have to necessarily do this. I think it's very helpful to relate your logarithms to your exponentials because I think the exponentials are more tangible. That helps you to construct the table of data that you then just plot your data points normally, right? You can see my data points here, and then sketch your graph from. Let me know if you have any questions. I hope that this helps. This is not a concept I expect you to get immediately unless you've actually worked with it before. So if you feel that it's unclear, I highly recommend going through it again. Write some of it out. Bring me questions. And I will see you on Thursday.